Okay, here's a strategy to solve an equation if an equation only has the variable written once. Just peel apart. That is, undo the last operation you see from the order of operations. So take a look here. In this equation, x is only written in one place. And so if we follow what would happen with this mystery number x, following the order of operations, we'd start with this x and then we'd subtract 5 from it. And then whatever number that is, the result is divided by 2. And then that value, this fraction, whatever number that is, we would add 4 to it. And then the result of that number is multiplied by 3. And then the result of that number, you subtract 6. So to peel apart, we've got to undo minus 6. So don't divide both sides by 6. To undo a minus, you've got a plus, right? So, um, so to undo this minus 6, you add 6 to both sides, and then you'll have, well, take a look down here, the first line of the answer, there's no more minus 6, and then the right side, well, we added 6 to both sides, so 12 plus 6 became, now you have 18 there. And now the last operation was a times 3, so to undo times 3, divide both sides by 3, that's why there's no more 3 on the left side, and then 18 over 3 became a 6. And now the last operation on the left side is a plus 4, so undo a plus 4 by subtracting 4 on both sides, then undo a divide by 2 by times 2 on both sides, and then undo a minus 5 undo a minus 5 by adding 5 to both sides. You'll have x equals 9 as the only solution. Okay, what do you do? So this is the best strategy to use if x is only written in one place. But what do you do if your original equation has more than one x written down? To solve an equation when x appears more than once, likely what you're going to need to do is factor. So just to spell this out a little more, after getting all the terms with x on one side and all the terms without x on the other side. So let's look at this example. Solve 7x minus 4 equals 3x plus 15. So all I did was I actually, for the first line of work, I just recopied this down, and I'd like to subtract 3x on both sides. Here, I am demonstrating the extreme use of parentheses. You'll see me sort of sometimes do this to show you what is technically going on behind the scenes, and sometimes you will see that I don't do this. But the parentheses are there, and it'll be important, we'll see, to just understand that they're there, even if we don't write them all the time. So this is what it looks like to wrap the original left side, original right side in parentheses, and then subtract 3x on both sides. We'll drop parentheses where we can, and so we'll have 7x minus 3x, and I've shuffled the order here, minus 4 is later. 3x minus 3x is gone. We're just left with 15 on the right side. Let's add 4 to both sides. Again, I've done this whole wrap the left side that was here in parentheses, and then a plus 4. Wrap the right side, which was just a 15 in parentheses, then do a plus 4. So the minus 4 plus 4 undo each other, and then 15 plus 4 on the right side is simplified to a 19. We're left with 7x minus 3x equals 19. So at this point, we have done exactly what the strategy up here says to do. We've organized our work so that all the terms with x are on the left side. Okay, and all the terms without x are on the other side. So on the right side, there's this 19, which doesn't have an x. Now what we do is, to really apply the strategy, we need to factor. That is, factoring is just undoing distributing. So we're using the distributive law, just sort of in reverse. Factor out x. So 7x minus 3x. If you factor out x, you have 7 minus 3 still in parentheses, and then when you factor, the thing you factor out, the thing that was common to both terms, is written outside parentheses. So 7 minus 3 quantity, then times an x. Leave the right side alone. So this is one equation turned into the next equation, and we didn't do something to both sides. We just used one of our true formulas to rewrite the left side. Now take a look in parentheses. 7 minus 3 is arithmetic we can simplify. So we'll have 4 for that. So 4 times still x equals still 19. Then divide both sides by 4. I wrote out the work this time of dividing by 4. And here's the thing. I have this 4x equals 19. I didn't just put a divide by 4 on both sides notationally here. I rewrote. It's like this work, 4x equals 19, I'm done with. I'm not messing with that line. On a new line, I've got 4x over 4 equals 19 over 4. Cancel the 4 on top and bottom of the fraction. Because it's just technically it's a 4 times x over 4 times 1, so we can cancel the 4 on top and bottom and be left with x over 1 equals 19 over 4, or we just often write x equals 19 over 4. I know this work as written is a lot of extra steps, okay? I'm showing the parentheses to try to really lead up to a thing we're going to see in a moment. Also, with this, I'm not expecting people to show all this fraction work all in the same way all the time, but I'm just pointing it out here so that we can connect it back to the fraction formulas we have seen. In the previous example, we did take 7x minus 3x. We rewrote this to become 7 minus 3 quantity times x using the distributive law, or by factoring as people tend to call it. And then we simplified what's in parentheses to get 4x. I will just point out that if you jump, so here's the work summarized. If you jump directly from 7x minus 3x to 4x, that is a thing that people do and call it collecting like terms. You may have learned it that in the past called that. But the only reason collecting like terms really works, the only reason it's a thing at all, is what we're really doing is factoring out x. Here's a second example. When you see 4x plus 5x and you say that that simplifies to 9x, that's true, okay? You might call this collecting like terms, but what's really happening is there is a skipped step in the middle, which you have to understand. It's required in this class that you know that when you jump from here to here, there is a skip step. I am not requiring you to show the skip step in your work all the time, but there are times where you have to know where this really comes from. This collecting is coming from factoring out an x and then simplifying what's in parentheses, because what's in parentheses is just plain old numbers with no variable. This is what's really going on. You have to know that collecting like terms is really under the hood. It's really, there's a skipped middle step of factoring out the variable. This will become very important in some work we see in just about a week or two. So while you generally don't have to show this middle step, if you don't know where collecting like terms comes from, for example, we'll get started right away. The next question type is going to be challenging. This should work out just fine. By the way, I've replaced all the x's with u's for this problem, but same idea. It's 1 plus 3 times u equals root 7 times u plus 9. This u here is not inside the radical. So I subtracted root 7u on both sides, and then I subtracted 1 on both sides so that all the terms with the variable are on the left and all the terms without the variable are on the right. I'll go ahead and even simplify 9 minus 1 to become 8. Now, students tend to really get stuck and freak out on this question because had this said 3x minus root 7x, people would be like, well, I would collect like terms had there been no radical, but I don't know what to do here is what I usually hear from people. But if you remember, as the previous slide just said, that collecting like terms is really, there's a hidden step. It's just factoring out the variable. Take a look at this now. So if you factor out u and you have in parentheses 3 minus root 7. That's a number. It's a funky number, but it's just a number. So the number in parentheses times u equals 8. So how do you undo this variable times this funky number in parentheses? You just divide by that number on both sides. Right? I kept this line of work alone. I didn't want to mess with it, so I kind of copied that down and then put each side over a 3 minus root 7, because now this 3 minus root 7 that's in parentheses, it's 3 minus root 7 times a u on top, and there's a 3 minus root 7 times a 1 on bottom, so these factors can cancel. And you're left with just a u on the left side. And on the right side, this is 8 over 3 minus root 7. Technically, later we'll talk about a way to rewrite this a little more simply, but let's not worry about that right now. The whole point right here is to say, let me step back to the previous slide. If you only think about 7x minus 3x is automatically, kind of like in autopilot, becomes 4x, without thinking about 7 minus 3 quantity times x, that is factoring out an x, you're going to get stuck here, right? You're going to get stuck right here and not see that this could be your next step. So please think about how collecting like terms is actually a trick that people learn. It's important to know why it works, and the reason it works is you're factoring out the variable. Okay, the numerator and denominator of a fraction, by the way, are always technically wrapped in a hidden set of parentheses. I say this just to point out it's not necessary for here, but other times this might come in handy. So this was a good time to talk about it. So for instance, what's after the equal sign here, I wrote in the middle. And if you wrap just the denominator in parentheses or wrap both the top and bottom in parentheses, these all mean the same thing. This is why in the denominator here, that's why we were allowed to just drop the parentheses. Okay, more generally, if you see a plus b over c plus d, technically the numerator and denominator are both in a set of parentheses. So if you were to write this using sort of the old school division sign, here the parentheses would be really required. Okay,